Okay, so last time we started talking about fingerprinting. And I gave you Freiwald's technique for matrix product, which involved fingerprinting by multiplication by a random, basically fingerprinting matrices by multiplying them by a random vector. And then we started talking about checksums, right? Where you're trying to send some length n string, which I can think of as an n-bit number. And you want to know that it arrived uncorrupted. Somebody after class asked me how you exactly use the checksum. And so I will remind you that you should ask your questions during class, because by the theory of random sampling, if you have a question, probably lots of other people in the class have it too. And therefore, you should ask it and benefit your classmates instead of learning the answer only yourself or expecting me to remember to answer it in class the following lecture. But in terms of the answer, checksums are used all over the place on the internet. One typical way to use a checksum is that you append the checksum at the end of the string, right? So you send your string, and we showed that you only needed an order log n bit checksum to check your number with high probability. This is because we only had n prime factors. And so if you pick a random prime in the range from 1 to n squared log n, will not divide the difference, right? In other words, we will not have the case that our prime divides the difference between the correct string and the incorrect string, right? If the string that was sent and the string that was received are different, then their difference is not 0, and the prime does not divide the difference, which means that if you compute the checksum of the string that was sent and you compute the checksum of the string that was received, they will be different. And that will tell you that the string that was received is different. Yes? So, as I was saying, one of the easy ways to make use of this is to just append the checksum to the string that you're sending. Another use is that you will just publish the checksum, right? If you're used to downloading software and stuff off of GitHub, each piece of software these days is published with a checksum so that you can make sure that the code that you downloaded hasn't been corrupted by somebody malicious, right? They're using cryptographic checksums. We talked last time about cryptographic pseudorandom generators. So again, a lot of the things that we prove work with high probability using some sort of random technique. In practice, what we do is use a cryptographic technique, and this is actually can be put on a sound theoretical footing by the sort of the research that has shown that certain cryptographic things cannot be distinguished from random things by a polynomial time algorithm. So if it works for random, then it will also work for these cryptographic sources. Okay? So that's where we left off last time, was for checksumming a single string. I'm going to apply the same technique to a sort of more general problem, which is text search. So the idea is that in text search, you start with some long string of length. Yes. You have your n-bit string, just as in the previous case. But now we also have an m-bit, what's called a pattern, okay, which is some substring that you are hoping to find somewhere in your string. So this is what happens when you hit Control F in your browser and you start typing. You want to find an occurrence of what was typed somewhere in the page, or everywhere that it appears in the page. Okay. Now, what's the most naive algorithm for doing this? Well, you compare the substring, right? So you've got your string of very long length. So what you can do is look at the string in positions 1 through m and compare that to your pattern, right? And then you can look at the string at positions 2 through m plus 1 and compare that to your pattern, and then 3 through m plus 2, and so forth, right? You're basically checking all the substrings of length m to see which of them match your pattern, right? And the runtime of this is order mn in the worst case, because you need to do your full, in the worst case, you're only going to find out it's not the right string at the end, so you're going to be spending m wasted time comparing to each substring, and there's n or n minus m substrings. Yes? So the question is, can we use this fingerprinting idea to improve the performance of this string matching algorithm? And so, you know, it seems promising, right? We want to compare things. We have here substrings that we want to compare. Maybe we can compare fingerprints of the substrings instead of comparing the strings themselves, right? And I should say this is the Rabin-Karp string matching algorithm. Okay. The idea is to pick your random p of order log n bits. And you know what's nice about log n bits is that it fits in a machine word. So it's normal to assume that you can do things like add them and subtract them and multiply them and so forth in constant time, right? That's not true of n-bit, right? Arbitrary long numbers can't be added in constant time, but we assume we have constant time operations in our machine. So we pick random p. We try to compute each substring fingerprint mod p, and we compare it to the pattern fingerprint. Right? So we already know that, you know, if we work with a random p, we're unlikely to be fooled by a string which is different from the pattern. We'll get a 0. We'll get matching fingerprints most likely only when the pattern is actually matching the substring we're looking at. But by itself, this doesn't seem to bias anything, because computing the fingerprint involves running through the substring, right? It's going to take us m time to compute each fingerprint. Yeah? But here's where Rabin and Karp had a clever insight, right? So suppose that I have, I'll work at the bits version. I have checked a particular substring, right? And now I want to check the next substring. Do I need to do all the work of computing this whole fingerprint from scratch? Right? What's the relationship between this fingerprint and this fingerprint? They have a lot in common. Can I exploit that in my fingerprint computation? So as you probably know by now, my algorithm is to call on the person who raises their hand the least first, and then I eventually get to everybody. But yeah, go ahead. Exactly. I mean, even before we start talking about mod p, right, the relationship between these two numbers is you subtract the most significant bit, if it's a 1, right? If it's a 0, you don't need to do anything, right? And then you double what's left and tack on the last bit, right? So next equals previous minus 2 to the m times the most significant bit of the previous times 2 plus the least significant bit of the previous, right? And if you're not working with bits, if you want to work with, base 26 for some reason, the math, you can do the same kind of math, right? Okay. But as you were saying, we're going to be doing we just need to do our arithmetic mod p, right? So we just put a mod p here, and now we have the next fingerprint based on, right, a multiplication and a couple of subtractions, right? 2 to the m can be computed once, mod p, and stored, right? You don't have to compute it every time, right? So you just subtract that if there's a 1 at the beginning, right? And then you double it. You don't actually even need to use multiplication, right? You can say prev minus 2 to the m times MSB plus prev minus 2 to the m times MSB plus LSB, right? So you don't have to multiply. You can just use addition, right? Now you also have to compute, you also have to worry about mod p, but the mod p computation is also not very hard, right? Because why is the mod p computation, I actually don't need to divide, I claim. Yeah? Exactly. I had something that was less than p, so I end up with something that's at most 2p. So at the worst, I just need to subtract p in order to get back into that small mod p range. Okay? So a couple additions, a couple of subtractions, and I have the next fingerprint. Right? So this lets us check all the fingerprints, all the substrings. In order n time, linear time, to scan the whole string for a match. Now, this is Monte Carlo, right? If I just tell you where there are matching fingerprints, I might be making mistakes, right? I might have false positives. Right, where the fingerprints appear to match. Right? If the fingerprints don't match, right, this is, again, one-sided error, Monte Carlo. Right? If the fingerprints don't match, I don't need to check that. I don't need to look at that substring. What if they do match? What if I want a Las Vegas algorithm? Yes? So if I wanted to amplify the performance, I could use a different p, which, again, like we saw last time, is basically the same as choosing p from a larger range. Right? When we did Freiwald's technique, we showed that if you use 0, 1, you get one kind of performance, and if you do many tries, it's like choosing from a larger set of integers. Here, too, you could use a different p for a second try, or just choose from a larger integer range. But that doesn't give me certainty. It just improves my confidence. Right? So how can I get certainty that I will only give you matching substrings? Yeah? Yeah. Just check it. Right? What does this do to the runtime? Yeah? It does nothing, right? The probability of a false positive is less than 1 over n squared, say. So the expected time of false checks is tiny, right? You do have to worry, though, about true checks, right? So if there are many actual occurrences of the substring, you will be confirming each of them through this. So if you have a string of all A's and you are searching for the substring of all A's, then for this Las Vegas guarantee, you would need to check every substring that it is in fact all A's, and this would take you back to order Mn. So the runtime is going to be order n plus m times the number of matches that you're looking for. Now, of course, if you're only looking for the first match, fine. If you want to return all the matches, this might become more expensive. Okay? Yeah, that's, yes, go ahead. No, we make it log of n squared bits. Right? Because if you remember from last time, the range that we need to choose from, right? We need to ensure that there are at least n prime factors, right? Or there are n prime factors that can trick us. And so we want to choose from a range of, say, n squared prime factors so that our probability of failure is small. Actually, I guess I wanted a 1 over n squared here, so I probably need to pick from a range of n cubed prime factors, which means that, you know, how big of a range of numbers do I need to look at in order to find n cubed primes? We said last time we need to look at numbers range from 1 to n cubed log n, right? So the maximum number I'm dealing with is n cubed log n. That still has log n bits. Okay. All right, so this seems pretty great, right? It's actually not the best string matching algorithm. If you decide to be smart about your string matching, you can go sublinear in many cases, not guaranteed. I mean, actually, the all A's string is still a kind of a bad example. But there are ways to skip a lot of the comparisons, if you think about it. Basically, if you're looking at the substring from 1 to m and you get a mismatch, it tells you things about the whole substring. You may be able to skip a whole bunch of the next substrings because you already know, based on their overlap with the first string, that they don't have the right pattern. And so there are some sophisticated algorithms, Aho and somebody, that essentially analyze the pattern very carefully to look at its own internal overlaps and build a skip dictionary that says if you get a mismatch at such and such a position, then there's no way you can have a pattern match until at least this far ahead. And so you actually jump forward over, you skip many characters of the string as you're doing the string match. And so this algorithm, that algorithm is actually interesting in that the longer the pattern is, the faster it gets because it can take bigger skips when it's hunting for a long pattern. So this is not the fastest, but this has some benefits that the other algorithm does not. One way it generalizes is if you're looking for multiple patterns. Right? You can sort of apply this, this same technique. And the point is you don't need to have a different fingerprint for each pattern, right? You don't need a different P, a different modulus for each pattern. You compute, you pick your random P, you compute the fingerprint of each pattern, and now you just, as you update your fingerprints, you're just checking, do any of the pattern fingerprints match the fingerprint that I'm computing incrementally, right? So even if you have many patterns, this algorithm is still quite fast, okay? It's going to be sort of n times the, the other way it generalizes is to two-dimensional pattern matching. So this is the kind of thing which might arise if you have an image and you want to find a particular sub-image in the image, right? So now you have an array of bits. And I will leave it to you to think about how you might use the same kind of sliding window trick in higher than one dimension. Okay. So, yes, go ahead. So the checking is already linear, right? You're just compare, right? You have an M-bit candidate, and you want to compare it to the M-bit pattern that you're checking. Yes, so if you're doing sort of searching for multiple patterns and things, then techniques like FFT can in certain circumstances be helpful. Oh, interesting. That's an interesting question. I haven't thought about whether, again, by pre-analyzing the pattern, you can sort of do the opposite of what the AHO algorithm does and sort of be confirming that several different overlapping patterns are all matches, several different overlapping substrings are all matches to the original pattern. That might be possible. It's an interesting idea. Okay. But the thing to remember is that in the usual cases, right, where there aren't aren't that many occurrences of your pattern, you're not going to have to do a lot of checking. So it may not be a thing that's worth investing a lot of time in improving its performance. Okay. All right. So now we've seen two different or three different fingerprinting applications, and I think you see the connections between fingerprinting and hashing, which we did before. Now I'm going to do kind of both of them at once. We're going to talk about something called Bloom filters. So we know there are lots of uses of hash tables, right? You put your keys in, now you can look up your keys. Usually, or in many cases, you associate a value with each key. And based on the key, you retrieve the value from the hash table. But one of the most basic data structures is just a set membership data structure, right? So suppose that you just want to be able to check whether you want to maintain a set and check whether a particular key is a member of a set. Okay. So you can certainly use a hash table for this, right? You can put each key that is in your set into the hash table, and when you want to know if the key is a member, you check if it's in the hash table. But this is a little bit inefficient, okay? So we can use a hash table, but suppose, right, a hash table does work for arbitrary keys, but suppose that my keys are just the numbers from 1 to n. Okay. And so I'm going to need a hash table that holds possibly n keys, but each of these keys has about log n bits, right? So I'm going to need to use log n, I'm going to use n machine words, but that means n log n bits to store the information about my set. If the keys are literally numbers from 1 to n, can you think of a more efficient storage mechanism than putting an entire key into a hash table? Yes? Map the keys to random numbers and take the XOR of what? That might be useful for telling me whether a set is, that might be useful for fingerprinting the set. But here I just want to know whether a particular number is in the set or not. Right? Well, again, if we're talking about keys in the range 1 to n, I don't really need a hash table, right? Yeah? Yeah, I could use an array, right? Just use an array of size n, right? I could put the keys in the array. But putting the keys in the array is overkill, because I just need to know whether they're there or not. So what values need to go into the array? 0 and 1. So I only need 1 bit for each key. right? So I can use a bit array, which is only going to take up n bits instead of n words, saving me a factor of log n. Okay? And this is often very important in practice, right? If you are building a web crawler, you need to know whether each URL that you encounter is already been crawled. You need to keep a membership directory of every URL that you've encountered, right? So multiplying those billions of pages by log of a billion dramatically expands your storage cost. Now, unfortunately, these URLs are not numbers in the range from 1 to n. But the question is, can we use this perspective that really you only need 1 bit per item if you're just checking membership, right? Can we use that perspective to manage keys instead of a closed range of numbers? And that's what Bloom filters are for. Okay. So let's see if we can kind of derive them. If we're going to start from this idea of we're going to just have an array of bits that are set to 1 to represent presence, right? Now we have this problem that our keys are not numbers that are associated with, that correspond to the bit positions, right? How can we therefore sort of map these big complicated keys to tell us where to look in the array? Yeah? Yeah, how about using a hash function, right? So what you could imagine doing is, you've got this key, hash it to an integer in the range from 1 to n, okay? And actually, let me start. I'm just doing this in order to match with my notes. So suppose that I have this array of m bits that I'm going to use to store presence. When I get a key, I just hash it to the range 1 to m and set the corresponding bit. And now I can, when I get that key again, I look in the table at that index and I'll see that it's set to 1, and that will tell me that I got that I had seen that key before, right? Okay, not a terrible idea. What goes wrong? Yes? Right, so we have the problem, as usual, of collisions. Right? It may be that some other key just happens to map to the same index, and so that index is set because of a different key instead of being set because of the key that we're checking, and so we could have a false positive in the Bloom filter where it tells us that a key is present even though it's not present. Yes? Okay, how can we cope with false positives? Yes? Good. So let's try amplification. Right? Let's skip over the obvious choice of make a bigger table, which will reduce your chance of collisions, but will also make you use more storage. Right? So let's keep the table size. But just try amplification. So what would amplification mean in this setting? It would mean maybe instead of having 1 hash function and checking 1 position, you have 2 hash functions, and you check 2 positions, right? So the idea of the Bloom filter is that you have k hashes, and you hash each item to k positions, and you set all those bits That's how you store an item in the Bloom filter. Conversely, when you want to see if the item is in the Bloom filter, you check all of the bits. So this is a classic use of amplification, right? There may have been some other keys that caused certain bits to be set, but if we're checking lots of different bits, it drives down the chances that all of the bits that go with our key have been set by other keys. Yes? Now, what is the problem with us setting many bits for each key? This solves a problem, but it creates a new problem. Yes. Exactly. We're going to fill up, we're going to set all the bits faster, right? If every time a key comes in, we set k bits, we're kind of using up the bits k times as fast, right? And if the table gets really full, then all of a sudden it starts to look like all of the keys are present, right? Because we're going to have a very good chance of all k of our bits being set. So there's this interesting tension now that if we use a larger k, it decreases our chance of being tricked in our checks, but it also leads to more ones in the table, which increases our chances of being tricked. And so we're going to need to do some optimization in order to figure out how to deal with that as best possible. So now let's do some math. We have a set of n items that we want to store in a Bloom filter. And I'm going to focus on the static case where, or at least the insert-only case, where we just want to put the items in. We're not going to think about deletion. Regular Bloom filters can't handle deletion, okay, although there are variants. So we set of n items, and we want to store a representation of these n items in a collection of m bits. Okay. And the way that we're going to do it is by by hashing each item to k bits. Okay. And m and n are given to us, but we can choose whatever k we want, and we're going to figure out how to optimize it. What was I going to say? Hash each item to k bits. Oh, yes. I am again going to use the uniform hashing assumption. It's actually very straightforward to show that you can use, your typical pairwise independent hash functions if you choose each of those hash functions independently. But I won't go into those details. Yes? No, you don't need to. Because remember, when you insert an item, you set all of its bits. So any item in this set will have all of its bits set. So the only way that you declare an item to be present in the set is if all the bits for that item are set. Okay? Oh, yes, I remember what I wanted to say. Under the uniform hashing assumption, I might hash a particular item to the same bit twice. It's fine. Actually, is it fine? No, it's not fine. I'm going to. No, the chances of a collision are going to be very small, and so they're going to get lost in the epsilons of the analysis. But I'm not going to do that detail for you. Okay, it just makes things messy without teaching you anything.
So sorry, Bob. I just left my car key.
Oh, well. Help yourself. You want to go home at 4 in the afternoon? I mean, don't you have to work? Okay. All right. How do we analyze this? The big question is around false positives. So we have a false positive if all k bits of a query are set. And so the question is, in order to understand the probability that all of our k bits that we check are set, we need to know how many bits are set, right? What we really want to know is what is p, right? The fraction of set bits, right? If p is the fraction of set bits, then each of my checks, right? Each of my bits is random by the uniform hashing assumption. So I'm checking k distinct bits, and the probability that I get, fraction of clear bits, again, just for consistency with my notes. Okay, so if p is the fraction of clear bits, then the probability of a false positive is what? Actually, I was right. You don't need to worry about collisions. Collisions are fine because of how we're doing this analysis. So I pick k random locations according to the uniform hashing assumption. What is the probability that I get fooled? Yes? Exactly. Okay, so now we just need to figure out p. How do I know what fraction of bits is clear? Yes? Yes? Exactly, right? So basically, we're inserting n items into the table, right? Each of those n items that we insert into the table leads to k hashes being computed and the corresponding bits set, right? So we are setting a random bit kn times, right? So if we make kn attempts to set a random bit, right? What is the probability that a particular bit stays clear? If we just set one bit at random, what's the probability a particular bit stays clear? Yeah? Exactly, right? Each time we set a bit, my favorite bit has a 1 minus 1 over m chance of staying clear, right? There's only a 1 over m chance that it gets picked. But this happens kn times. So using my favorite approximation, e to the minus kn over m. Yes? No, I actually went back and fixed that, right? So we're hashing each item into k bits, and if it hashes to the same bit twice, I don't care. I'm just going to, it's just k distinct hash functions. Yes, but each of the things that we check is a random choice. Right? Okay, so this is the probability a bit stays clear. Is this equal to p then? Well, unfortunately not quite, because p is actually a random variable, right? So maybe this is more like the expectation of p. And we even have to be worried about that, because the bits staying clear those aren't independent events, right? Yes. Kn, I think, is often going to be larger than m. Okay. So we have this thing to worry about, that maybe we don't quite have p, but let me not worry about it for a minute. Let's just say, you know, in a perfect world, these things would be independent, and this would be the actual value of p, right? This gives us enough information to figure out how to set our k. Okay. So we want to pick k to optimize. What do we want to optimize? We want to optimize the chances of a false positive, but now we can plug in our value of p. Okay. Yes? Yeah? Yeah? We are picking randomly, but if I tell you that all of these bits are clear, well, nothing's going to hash them, which means that the other bits are more likely to be set, right? Because I have to set kn. I have to do kn settings. And if I didn't set things here, I must have set them somewhere else. So those other bits become more likely to be set. Okay? This is the same argument, the same issue as we saw in balls and bins, right? That the emptiness of bins is not entirely independent. Okay. All right. So if you do the obvious thing, you take the derivative and set it to 0 and so on and so forth. What you find out is that k should be set equal to m over n times the natural log of 2. Okay. Now that seems like a weird number. But if k is m over n times, if k is m over n times the natural log of 2, what does that do to p? Yes. Yeah. This implies that p is equal to exactly a half, which for a theoretician makes a lot of sense, actually. Okay, why would it make sense for p to be a half? Has anybody studied information theory? Yes? Exactly, right? So if you've studied information theory, right, an unbiased bit is the one that carries the most information, right? Another way to look at it is that, like, if p is very close to 0, right, so that most of the bits are set to 1, then you don't actually get m bits of information, because it's cheaper to just tell you which are the clear bits, right? Similarly, if most of the bits are set to 0, it's just cheaper to tell you which are the set bits, right? So the maximum information is present in your data structure if each of the bits is 50% likely to be set. Not important for our analysis, but a sort of interesting tie-in. Okay. So if you if you put p equal to a half like this, then the false positive probability f is equal to 1 minus p to the k, which turns out to be about 0.6185 raised to the m over n power. Okay. So for example, if you set m equal 8n, you use 8 bits per item, then your false positive rate is 2%. Okay? And basically, you figure out what false positive rate you can tolerate, and that tells you how small you can make your Bloom filter. And of course, as is usually the case, the error rate decreases exponentially in your parameter, right? If you double the size, you're squaring the false positive rate. So you get rapid returns. Okay. So, the way you use Bloom filter is you do need a way of handling the false positives, right? So if we go back to the web crawler example, right? You would not want to use a false positive rate of 2% in that case, but in the web crawler example, you check in the Bloom filter for whether you've seen that URL before. If the Bloom filter says yes, then you go to your database and check if you've actually seen that URL before. And that's a very expensive operation because that information is stored on a storage device instead of in memory. Right? The goal here, the idea here is that you fit the Bloom filter in memory and access it often, and every once in a while there'll be a false positive that will force you to go off to the storage service. Okay, and based on the relative costs of how slow is your storage device, that will tell you how you want to set your false positive rate. Okay, so we happy with the general analysis and demonstration that you can get useful false positive rates from a Bloom filter without using a lot of space. What I want to do now is fill in this assumption that I made about independence of empty bins so that we can argue this is actually working. Yes? Well, then you would need log n bits. So again, Bloom filters are maybe not that exciting from a theoretical perspective because in order to get a 1 over n false positive rate, since you're raising a constant to the power of m over n, you would need m to be about n log n, at which point you could just use a hash table.
And what about having a hash table where you don't store the initial key, but you just store hash at the location?
Yes, so there are many interesting variants of Bloom filters. I'm staying focused on the simplest one. There are some where you don't just set bits, but you have counters, small counters in each position. Instead of just a 0 or 1, you might have something that goes from 0 to 8. There are cases where you store little fingerprints of the item instead of storing the actual item, right? And all of these can lead you to different kinds of trade-offs of false positives, and some of the generalizations can also allow you to do deletion from a Bloom filter. Do you see why deletion does not work in this design? What's the problem if you want to delete an item? Yes?
For each hash, whether you should clear or not, because it could clear by this element, you're dealing with other elements.
Exactly. You could.
Fix it is by counting elements.
That's why I said in some cases you add in some cases you put counters in to support this kind of deletion operation, right? So, but in the basic Bloom filter, if you want to delete an element, you would clear all of its bits, but that's not correct because those bits might have been set by a different element, right? Okay, so let's talk about this independence assumption. So draw a picture. We're basically looking at a balls and bins problem again. Right? We've got our n bins, and wait a minute, it's m bins. We've got our m bins, and I'm putting some number of balls, bit settings, into the bins. Right? I'm going to denote that by alpha m balls that are being dropped into the bins. Okay. We said before that since these balls are all going in at random, the probability that a bin is empty is 1 minus 1 over m to the alpha m, which is about e to the minus alpha. I'll also just mention that the expected number of balls in a bin is equal to alpha, right? And this is true for any one bin. The problem is the dependencies between the bins. So in order to get around this problem, well, actually, let me tell you something that seems unrelated for the moment, but is relevant, which is, let's talk about the median of the binomial distribution. So if we go back to talking about B of NP for a minute, we know that the median, or sorry, the mean, not the median. We know that the mean is NP. But what can we say about the probability that our outcome is equal to the mean? I'm actually going to claim a lower bound of at least 1 over the mean. For now, think of this as some interesting trivia about the binomial distribution. I will use it in a minute. Okay? But basically, the probability that you hit exactly on the mean is 1 over the square root of the mean. And what is interesting about this is that it doesn't depend on n. Right? Even if n gets really, really huge, so that there are many possible values that you could attain, right? The probability that you attain the mean value is still 1 over the square root. So if the mean is small, you have a good chance of attaining it, even if n is huge. And actually, in a sense, we already proved this, because we know from the Chernoff bound that we have this e to the minus epsilon squared times mean divided by 3. Sorry, let me put an omega here. So we have this probability of deviation by 1 plus or minus epsilon from the expectation, right? And the point is that this becomes large when epsilon is bigger than 1 over the square root of mean. In other words, all of your probability is in NP plus or minus order square root of NP, right? And if all your probability is there, right, this is only square root of NP different values, right? And so at least some of them have to be large. It's also not hard to show that the mean is the maximum value in the distribution. So basically, the very coarse picture of a binomial distribution is that its probability is essentially 0 outside of an interval of length square root of NP. And all of the probability is in this interval of size of width root NP. And so the things in there have a probability of at least 1 over the square root of NP. All right? Now, I actually can fill this in with a little bit more careful mathematics using Stirling's approximation. So what we're interested in is the value of the binomial distribution at the mean. Yes? Now, this can be written as n factorial over np factorial times 1 minus np, n minus np factorial. And now we use Stirling's approximation, which says that n factorial is theta of root n times n over e to the nth power. Okay. I'm assuming most of you have seen Stirling's approximation before. So if we plug that all in, everything works out just fine, right? So we have root n times n over e to the n. Then underneath we have root np times np over e to the np times the square root of n minus np times n minus np over e all raised to the n minus np. And then we multiply that by p to the np times 1 minus p to the 1 minus np. And now everything starts to cancel out very nicely, right? So we have an n to the nth power up here. We also have an n to the np power and an n to the n minus np power, so those all cancel out, right? And so this becomes p over e to the np, but that the p cancels with this p to the np, right? Similarly, this this becomes 1 minus p to the n minus np, and that cancels with this one over here, right? And so at the end of the day, all you're left with is actually these square root of n terms, right? And so all that's left at the end is one extra square root of n term in the denominator, or sorry, square root of np term in the denominator, and that's the probability. That's the value of this binomial term. Okay? I'm hoping nobody needs to see me work out the math, because I'll probably get it wrong. But everybody buys this. So now I've proven this claim that the probability of achieving the mean is about 1 over the square root of the mean. So how am I going to use that? Well, we want to analyze clean bins, or empty bins. We have this problem that there's a dependence. I'm going to change the experiment so that we have true independence. So instead of imagining that I'm throwing just alpha m specific balls into the bins, right? What I'm going to do is I'm going to create for each bin its own set of balls that might land in that bin. And if they don't land in that bin, they don't go anywhere. It's not like they're choosing which bin to land in. They're just choosing whether to exist and land in their bin. So I couldn't resist calling these the possiballs, right? That might be there or might not. Okay. But I'm going to set this up so that the numbers work out the same. So I'm going to consider some very large number R of possiballs for each bin, right? But each of them lands with probability alpha over R. Why did I decide to make the landing probability alpha over R? Well, because that's what it is in my original, that gives me the appropriate mean number of balls per bin. Okay? So under this experiment, it is also true that the expected number of balls per bin is alpha. Yes? Now I'm going to let R go to infinity. Okay? This is going to let me ignore sort of annoying cases because their probability will go to 0. Okay. So what can I say about the probability that a particular bin is empty? If I have R balls that each decide to go in with probability alpha over R. Yeah? Which is, again, the same as my original analysis. Okay? So under this experiment, I have the same probability of an empty bin as in my previous analysis, but all of the bins are independent, so I can really say, right, so the bin empties are independent. So with high probability, the number of empty bins is 1/2 plus or minus, or n over 2 plus or minus root n by the Chernoff bound. Right? So if I could do this experiment instead, I would know that with high probability I have just about the right number of empty bins. Does everybody buy that? Now what I'm going to do is tie this argument back to, I'm going to connect this back to the original experiment, right? So suppose that exactly alpha m possibles materialize. If I condition on this event, I claim that I am running my original experiment. Okay? Because each of these possibles is making an independent choice about whether to materialize or not. Right? If I tell you how many of them materialize, which ones it is can be determined by just choosing randomly from among this set of possibles. Right? So if I choose a random possible, what I'm actually doing is putting a ball in a random bin. Right? Now you might complain that once I've chosen one possible from a column, it decreases the chances of choosing another one. But remember, I set R to infinity. So the odds that I am, and notice I'm picking a finite number of these balls, right? Alpha m. So as I move R to infinity, the fact that I've chosen a couple of balls here doesn't change the probabilities at all. Okay? So if I get exactly alpha m possibles, then I would be running the original experiment. Okay? Now, what is the probability that exactly alpha m possibles materialize? Well, the number of, what distribution does the number of materialized possibles have? Yeah? It's binomial, right? It's a binomial where I have Rm possibles that each appear with probability alpha over R. So its mean is alpha m. So this is just the probability that the number of possibles matches its expectation, which we just argued was at least 1 over, or omega of its 1 over its expectation. Yes? So there is a decent chance that I get exactly the right number of possibles and then proceed to run the original experiment. Okay. Now let me wrap up this argument. We wanted to argue that there weren't too many set bits, right? Now, I'm going to start by analyzing this in the possibles setting. Actually, let me put it a different way. We know that with high probability, there are not, let's see how, tangling myself up. So I'll do it by contradiction. Suppose that there is a large probability of too many set bits in the original experiment. Yes? I'm going to prove that that can't actually happen. Okay? Because the probability that wait a minute, which way did I go? Right. So the probability that there are too many set bits in the possibles experiment is at least the probability that too many set bits in the possibles experiment conditioned on having exactly alpha m possibles materialize times the probability that we get exactly alpha m materializations. Right? Now, we just argued that this probability was at least 1 over the square root of alpha m. On the other hand, we argued that this does not happen with high probability. Right? Because here we were able to use the Chernoff bound. So, if we were likely to get too many set bits when we have exactly alpha m, right? And this is the original experiment. Right? So if the original experiment was likely to produce too many set bits, then you would be right? So essentially, you know, here we say probability less than 1 over n cubed, say, or 1 over m cubed, right? So this had better be less than probability 1 over n squared, because if it's bigger than that, you will end up with something that's bigger than 1 over n cubed when you multiply by this other term. Okay? So essentially, what I'm arguing is that there's enough connection between the independent case and the non-independent case that we started with that you can't have a bad event in one case without it also being likely in the other case. Okay, I saw a hand. Yeah, go ahead.
I guess
That is correct. But what I'm saying is that if you add this conditioning event, it becomes the same experiment. Right? adding conditioning makes these set bits not independent. Okay, and that's why it becomes the original experiment, or they're not independent because it is the original experiment where they're not independent. Okay? Right. So, this is a relatively minor point. I could have just sort of waved my hands and said that it's not that big a difference whether they're independent or not. I wanted to prove this to you because it's an interesting technique of sort of connecting, right, between a distribution where things are independent, and so it's easy to analyze, and another distribution where things are not independent, but where there is enough of a tie that you can draw conclusions about the dependent case from the independent case. I will also mention that this model of using this probability alpha over R and letting R going to infinity, what that yields is what's known as a Poisson process. And the probability that you get exactly k balls is equal to e to the minus alpha times alpha to the k over k factorial. Alpha is known as the rate of this Poisson process and is also the mean of the Poisson process, right? So this trick didn't come from nowhere. It's a standard way of deriving the Poisson process as the limit of a binomial distribution. Yes?
The first question is, even when we condition the Poisson theorem on exactly alpha n, does the statement about the n still apply?
Which statement?
You said the high probability that x of n is about like n over 2 for x.
It applies because if it didn't, we'd be running into a contradiction with, right? So this statement is a statement about the independent case, right? What I'm arguing here is that with reasonably large probability, the independent case looks like the dependent case. And therefore, if something happened in the dependent case, it would also be happening reasonably often in the independent case. All right? But we know that it can't happen, that it does not happen often in the independent case, and therefore it does not happen often in the dependent case.
Okay. Yeah, because okay. And then the thing that we proved, and then that was what we were saying. And we say this happened that was
Yes, exactly, right? In the independent case, each bin can be considered independently. It has a certain probability of being empty. The Chernoff bound applies because the emptiness events are independent, and so we immediately derive this result from the Chernoff bound. Okay. Yes? Let's see. I mean, it's funny. It comes under the general name of the Poisson heuristic. And you can find you can find an application of it to the coupon collector problem in the Motwani-Raghavan textbook. And I think it's the kind of thing to think about whenever you're in a situation where things are almost independent, right? Where your intuition tells you that there shouldn't really be a lot of dependency between them. Then you can consider generating a related experiment where you've removed the dependency and you can put it back by some sort of conditioning. Okay? All right. Sorry, I lost track of time, and your break is coming at the end of lecture. So I will not be... so on Friday, we will switch to one of the weirdest applications of fingerprinting I've ever seen, which is solving bipartite matching problems. How could you possibly use fingerprinting to solve a bipartite matching problem? Well, come on Friday and I will show you.